So yesterday we looked at solving what I call basic trigonometric equations. And I guess I can give you some steps for solving these. There's kind of two approaches though. There's one approach for people who are not familiar with the unit circle. Good afternoon, Josh. And that approach is kind of a three-step approach. And even if you are familiar with the unit circle, you have to do what I'm about to explain from time to time. And I'll get into in a second when you can just go to the unit circle as opposed to doing what I'm talking about. The first thing that you need to do is find a reference angle. So for the explanation purposes here, I'm going to make up a trigonometric equation. I'm going to write cosecant of theta equals negative 1.2. And in order for you to determine a reference angle for that trigonometric equation, the first thing you need to actually do is rewrite it as a primary trigonometric ratio. Since cosecant and sine are reciprocals of each other, we can write sine of theta is the reciprocal of negative 1.2, which is negative 1 over 1.2. Again, I just prefer to put that negative on the top. And now I find the reference angle. I'll do my work in blue. So step one is to find a reference angle. Oh, let's add one other thing here. Let's say that we want theta between 0 and 2 pi rads. So that statement is saying theta can equal 0 or it can be greater than 0, but it must be less than 2 pi. So I'm going to find the reference angle by taking the inverse sine. Let me get this out of the way so you can see the equation. The inverse sine of 1 over 1.2. Remember that when you find a reference angle on your calculator, you never put in a negative even though the trigonometric ratio may be negative. So this negative here is not going into the calculator. I'm only using an example with radians because you have to get used to thinking in terms of radians. So put your calculator into radian mode, and we take the inverse sine of 1 divided by 1.2, and you get a peculiar looking angle. But don't forget, this is in radians. You get 0.9851 radians. And we don't need to write rad because if we don't put units, the rule is it is radians. Now on to the second step. The second step is to sketch the reference angle in the what I will call appropriate quadrants. And we don't have to go back and look at the cosecant statement to determine the appropriate quadrants. What we can do is say that since sine was negative, and sine is defined in terms of y and r, we're looking for quadrants where y is negative. R, of course, is always positive. So this next step involves actually a couple of steps. I suppose what you need to do first is identify the quadrants, and it is going to be quadrant 3 and quadrant 4. Those are the two quadrants where y is negative. And now we sketch that. So in quadrant 3, we have a reference angle of 0.985. And in quadrant 4, we have a reference angle of 0.985. Now, I don't really have any good idea of what 0.985 radians looks like. Well, I do, but as a student, you might not. It doesn't matter if you know what 0.985 radians looks like. What matters is that you draw it in the appropriate quadrant. Your last step Once you've done that, is to determine from your diagrams theta. And when I write theta, I'm talking about rotation angles. I say angles plural because you're going to have two of them. And I'm just going to highlight them in a different color on my diagram. Before I do, again, I want to impress on you the fact that this arc that I drew and this arc that I drew is non-directional. There's no direction associated with it. It's just an angle. However, when I draw the rotation angle, I need to say that the rotation angle is this, that's theta, that's one of them, and this. So in the case of the quadrant 3 angle, theta can be found by taking pi radians plus the reference angle. And in the case of the quadrant 4 angle, theta can be found by taking 2 pi minus the reference angle. And that's where you just go to your calculator and do it. So pi plus the reference angle gives me 4.13 radians for the first angle, and 2 pi minus the reference angle gives me 5.30. So 4.13, 5.30. So before I get to questions, I do want to spend some more time reviewing this. I told you that you could rely on the unit circle, that certain people are capable of relying on the unit circle. But the fact of the matter is the unit circle is useless in this question I made up. And the reason for that is, maybe just take your calculator right now and calculate for me what negative 1 over 1.2 is. When we do that, you get negative 0.83 repeating, I think. You get 0.83 repeating, and although that is a y-coordinate on the unit circle, it's not one of the y-coordinates on the unit circle that you are familiar with. It's not 1/2. It's not root 2 over 2. It's not root 3 over 2. It's some number that we're just not comfortable working with. However, if you have a question like, well, I'll pick on D here, and in fact, I want to do D with you. I want you to work through D with me as well. I said don't worry about D because of the negative angle in the domain. And after giving that some thought, I think we have time today to talk about it, and I think it's a valuable mental exercise here. So we're going to do D here so that we can learn about how to deal with a negative number in the domain, and so I can review how to use the unit circle if you want to use the unit circle. So your first step is to write secant of theta equals negative root 2. And to turn that into an equation that's a primary trig equation. So you can look at your formula sheet, or hopefully after a while you just know that the reciprocal of secant is cosine. So cosine of theta is negative 1 over root 2. Now, for those of you that are good with the unit circle, this is enough information for you to find the positions. We are going to have, and when I do it with the unit circle, by the way, I don't draw two diagrams. I draw a single circle, and I say that cosine on the unit circle is x. So where is x on the unit circle? Negative 1 over root 2. Well, I know that the 1 over root 2 numbers are the 45-degree numbers. So this terminal arm will pass through an x coordinate of negative 1 over root 2. quite frankly, I don't care what the y-coordinate is, but I'll write it down anyway. It's 1 over root 2. This terminal arm will pass through a point whose x-coordinate is negative 1 over root 2. And again, I don't really care about the y-coordinate, but I will put it in anyway. It's negative 1 over root 2 as well. So these are the two positions. And I talked about this yesterday. I want to stress it again. Those 2 points I'm not calling angles yet. They are positions or locations. Okay. Now, for those of you that are going to use a calculator, you're not comfortable with the unit circle, you would take the inverse cosine of 1 over root 2, right? You would disregard this negative. And let's say you wanted to do this in radians, which you do. This question says we want it in radians. One of the many things you have to remember in this unit is that even though we want an answer in radians, since it has to be an exact value, we need to opt out of the radian mode and put it into degrees just so we can recognize the answer. Just quickly here, if I'm in radians and I take the inverse cos of 1 divided by the square root of 2, I'm lost. I don't know what that is. I don't know where that is. But if I'm in degrees, and this is only the case if we're after exact values, and I take the inverse cosine of that and get 45 degrees, that's meaningful to me. So then what I do is I draw my 2 diagrams with a 45-degree reference angle. So we cheated. This is 45 degrees, and then you just say, well, that's pi over 4. We draw it in quadrant 2 and in quadrant 3, and these are the 2 locations. I hope it's pretty clear that when I looked at my unit circle, the 2 locations I got are the same as the 2 locations I got if I use my calculator and a reference angle. Okay, now, what we would normally say here, everybody, is we would normally focus on this as an angle and this as an angle. But since the domain is negative pi to 3 pi over 2, we have to also consider going in the other direction with negative angles. So one of the angles is from here to here, and you should know that's 1, 2, 3 pi over 4. That's this angle in the bottom set of diagrams. One of the angles is from here to here, and that is 1, 2, 3, 4, 5 pi over 4. And that is this angle in the bottom diagram. But one of the angles is from here to here, which is negative 1, 2, 3 pi over 4. Now, could we also, and by the way, that's this, could we also go from 0 in a negative direction all the way to here? Well, you could. That would be negative 1, negative 2, negative 3, negative 4, negative 5 pi over 4. But that's not in the domain. That's past negative pi. So I really don't think it's that difficult to do problems with negative numbers in the domain as long as we're looking at exact values. Anyway, that's my review of yesterday. So before we get started with questions, a couple of things. I'm going to do my best to have your assignments, which should be in now, marked by the end of the day tomorrow. In your individual folders, you will find your next assignment, and I need to talk to you about that. Even if we were still in school, I had adjusted my course delivery so that we were not going to have an exam in polynomials. And that means when we get back, we're still not going to have an exam in polynomials. The assignment that's currently in your folders, assignment number 2, is an exam assignment. You don't have to write it under exam conditions, but when you turn it in and I mark it, that's the mark that's going to go in for the polynomials exam. There are no rewrites on that. So you have almost a full week to get it in. I think I put next Wednesday as a due date, and there are 2 written response questions. So it's important for you to take that assignment seriously if you want to do well mark-wise. The second thing is, if you looked at your Google Classroom post today, we're only doing 1 lesson today. And we're probably only going to be doing 1 on Monday. I really feel that these next few lessons that we do, if we try to do 2 in 1 day, the wheels are going to fall off the bus. It's going to get pretty ugly. So now, does anybody have any questions from yesterday's assignment that you would like me to go over? All right. If not, we're going to move on and look at solving what I call complex trigonometric equations. So this is section 4.4. Notice, by the way, section 4.4 I call an introduction to trigonometric equations. Even though the equations we look at today are more complex than yesterday, it's still an introduction to them. In the next unit, we will talk in more detail about trigonometric equations. And again, I'll just remind you, I think you guys know this, but if you do have a question during the course of the lesson, please interrupt me by using your mic or typing something in the chat. And if I don't notice the chat right away, then somebody let me know. I've got the chat open on another window right now. So we're looking at solving more complex trigonometric equations over specified domains and also over the domain of all real numbers. I want to spend some time with you reviewing algebra. And I really believe that what I'm about to go through with you is crucial to your success in this lesson. What you're looking at on the board are 3 different quadratic equations. The first quadratic equation is 2x squared minus x minus 1 equals 0. And there is a quadratic term. There is a linear term, and there is a constant term. You should know these terms, these words from polynomials. X squared is quadratic, x to the 1 is linear, and x to the 0, which is what that 1 is constant. When you look at the quadratic equation to the right, there's a quadratic term and there's a linear term, but there's no constant term. So the first equation has a quadratic, a linear, and a constant term in the equation. The second equation has only a quadratic and a linear, and the last equation has a quadratic and a constant. And very often, it's going to happen to almost everybody, as soon as you run into a quadratic equation like this one that's missing a constant term, or like this one that's missing a linear term, you forget how to solve them. So I want to review how to solve these 3 types of quadratic equations. If you were going to solve, I'm going to call the top left one, number 1 rather. So if you're solving equation 1, hopefully it's factorable. And I would like everybody to take a second here and FOIL out mentally or on paper 2x plus 1 multiplied by x minus 1 and confirm that you do get 2x squared minus x minus 1. And once I get some people confirming that, I would appreciate it if you would let me know through chat that you're getting that 2x squared minus x minus 1. In other words, I want you to confirm that it's factored correctly. And the expectation is that you can factor 2x squared minus x minus 1. So where does that take you? I've talked about this a lot in my math classes. This philosophy I have in math education. This is a grade This is a grade 11 math problem, 2x squared minus x minus 1. And in some ways, it's still a grade 11 math problem until you're taught in grade 11 that since this is a product of two things that gives you 0, as long as one of them is 0, the equation is true. So if 2x plus 1 is 0, if this thing is 0, then 0 times the x minus 1 gives you 0, and it's true. If this thing is 0, well then, if x minus 1 is 0, it doesn't matter what 2x plus 1 is, because you're going to be multiplying it by 0 to get 0. And what I'm saying essentially is we've gone from a Math 11 question to, you know what, to be honest, a grade 7 math question. I mean, finding out what x is in these two simple equations, grade 7 students might not be taught the formal rules for rearranging, but they can figure it out. And what you discover is that x is equal to negative 1/2 and x is equal to 1. So I'm just reviewing how to solve that quadratic equation. Now, when people get to the second quadratic equation, the one in the top right, some people are confused, and what they try to do, unsuccessfully almost all of the time, is they think that they're going to factor this in the same way they factored the one on the left. They're going to try putting numbers here and here, and 4x here and 4x there, and it's a mess. And the reason is you don't do that. You still factor, but you take out a common factor. This is something you need to, I think, really drill into your head. If there's no constant term, you factor a common factor out. And there's always going to be a common factor because both terms have x. And now we do the same thing that we did on the left. We say that the first factor, which is 4x, equals 0. So there's one factor of 4x multiplied by another factor of 4x minus 1. So you set each factor equal to 0, and you solve these. You get x equals 0 and x equals 1/4. I hope you're still with me, because when we get to the bottom equation, this gets even more confusing. People don't know what to do here. And you solve an equation that has a quadratic and a constant term, not by factoring, but by rearranging. All you have to do is move the 5 to the other side and divide by 3 to get a statement that says x squared equals 5/3, and then boom, you have your answer. X equals plus or minus the square root of 5/3. So, you know what I would recommend here, everybody, because this is not in your notes, I don't think. Is this in your note package?
No.
No. So what I would recommend here, and you can always watch the video later, but is to take your phone right now, if you're looking, if it's possible, and just, if you're watching on your phone, take a screen capture of it, or if you're watching on a computer, take a photo of it. This is kind of the template for how to solve different quadratic equations. So what I'm going to do is leave this up here for about 30 seconds. While you're waiting, I can tell you a joke. Did you hear about the magic tractor? No? It turned into a field. It takes a while. If you don't get it right away, sleep on it. And I guarantee you, once you get it and appreciate it, you'll be telling all your friends. Crickets, yeah. Ba-da-ching. Okay, let's move on. So again, this is going to get ugly very quick. I have a different equation here, by the way. This 2x squared plus x minus 1 is different than what we had here. This example was 2x squared minus x minus 1. So solve the equation shown below. This should be like stealing candy from a weak and tired baby. X equals 1/2 and x equals -1. There should be absolutely zero problems in solving those two linear equations. Now, you already know the point I'm going to get across here, I hope. When you have this quadratic equation, your first step is to factor the quadratic equation. So we know that 1 and 1 have to go here and here, and the 2x and x have to go where I wrote them. With a little bit of thought, I can see that if I put a positive here with the 1 and a negative here with the x, you certainly don't have to write this every time, but you know, when I take that and in my head I FOIL this out, I get 2x squared plus 2x minus 1x minus 1, and that makes me very happy because that's what I had up here. 2x minus x is positive x. So the bottom line is you factor it, and then what you do is you set those two factors equal to 0. Again, I hope I'm not telling you something that's new to you. I'm reviewing a very basic concept with quadratic equations and factors. So I'm going to add 1 to both sides and divide by 2, and I get x equals 1/2, and then I get x equals -1 here. And the point is that since these two linear equations contain the factors within the quadratic equation, the two solutions for the linear equations are the solutions for the single quadratic equation. The lesson is, if you have a quadratic equation, you factor it and solve the linear equations that result. So to solve any trigonometric equation that's quadratic, that's right. A trigonometric equation that's quadratic is what we're going to be looking at solving. You want to, in general, factor it so that you have two factors. So this isn't going to be 2x and 1. It's going to be expressions with sines and cosines and tangents and cosecants and all of that. But once you do factor it, the first linear factor, set equal to 0, will give you a solution. Well, I'm going to repeat that and change what I said. The first linear factor 1 equal to 0, will give you solutions, and linear factor 2 will give you solutions. The equations we solved yesterday are these. This is a basic trigonometric equation. This is a basic trigonometric equation. And those basic trigonometric equations from yesterday had multiple solutions. Some of them had two locations that made it true. So, solve, I don't know why I have a comma there, being overly zealous with the English language, solve 2 sine squared of x. So that's how that's pronounced. This is pronounced, I'm going to erase this, but I just want to make sure that you see what I'm saying. Is there two N's in pronounced? Like, is it P-R-O-N-N? You know what, I don't care. It's a math class. Pronounced sine squared of x. Okay? What it means is sine of x quantity squared. And the reason we pronounce it as sine squared of x rather than saying sine of x squared is if somebody says sine of x squared, they mean that. So whenever you see something like this, this is sine of x squared. When we want to say we're squaring the whole trigonometric ratio, we say sine squared of x. So that's just a quick briefer on how to pronounce that and what it means. So this is quadratic because there's a squared on a variable. That means I have to zero the quadratic equation and write 2 sine squared of x minus 1 sine of x minus 1 equals 0. Now, every time I have to teach this, I'm always torn between the two methods, because if I show you one of the methods, I ruin the surprise of the other method and vice versa. So I just tend to toggle back and forth from semester to semester between the methods. I'm going to show you the Math 30-1 method first. This is what I would hope everybody can do. Since this is a quadratic term, and this is a linear term, and this is a constant term, that means if it's factorable, it will factor into two binomials. And incidentally, let's do a b squared minus 4ac test. B is -1 squared minus 4 times 2 times c is -1. Take a minute, please, and calculate for me what b squared minus 4ac is, and go ahead and start typing your answers of what you get. And be honest with yourself. Don't look at what other people are typing. Calculate it, and then let me know through chat what it is. Sure, it's 9. B squared is +1 minus -8 gives you 9. I'll just squeak it in here because I don't have a lot of room. I guess I do. And 9 is a perfect square. So this is factorable. So this is what a Math 30 student and a post-secondary student and a calculus student says. They say, I must put a 2 sine x here and a sine x here. I have to break up the first term that way so that the product of these two will give me the 2 sine squared x. But I also need to break it up that way so that my inner will be sine x terms and my outer will be sine x terms. In other words, I can't put 2 in the first set of brackets and sine squared in the second. And then we factor it in the same way we would if it were non-trigonometric. We say, well, I need a 1 here and a 1 here. And then I start playing around with the positives and negatives until I can arrange it so that it works. If I were to FOIL this out, and I get that some of you get this already, but I need to explain it for everybody. If I were to FOIL this out, my first would be 2 sine squared of x, and that's correct. Okay? My last would be 1 times 1, and that's correct. Now, obviously, one of those two numbers needs to be negative to give -1, but I worry about that later. I'm not so sure we need to check the F and the L. Of course, these two are going to work out. That's why we chose these numbers, so that we would get 2 sine squared and 1. Now we do the outer. So I'm taking 2 sine x times 1, which gives me 2 sine x. And I take my sine x times 1, which gives me sine x, and I ask myself, can I combine these two terms to get -1 sine x? And the answer is yes. I just have to make sure that the 2 sine x is a negative, and then they will add to give -1 sine x. And then I reverse engineer it. I say, well, where did the 2 sine x come from? It came from the product. I'm making a mess here, but it came from the product of these two. And that means that the only way to get -2 sine x is to put a negative in front of the 1 on the right and a positive over here. And now we're done factoring it. For those of you that have no problems factoring that, I would say if you have no problems factoring it, you should have had it factored about 2 minutes ago. But for those of you that understand this, be patient, because this is really confusing to a group of students. So the other alternative is to do the following. We had, so if you are at all confused with this factoring, you're going to have to do the following. 2 sine squared x minus sine x minus 1 equals 0. And what you're going to do is you're going to let sine x equal something. It's just a letter, okay? R. Don't say x. Well, that means that this equation becomes 2r squared minus r minus 1. And again, for people that can factor this, it's hard to imagine how changing this to r makes it easier, but for some people it does. Now, you factor this instead. Do a little bit of thinking, and you do that. And then what you do, and again, if you can factor it without doing this, you're kind of rolling your eyes maybe and saying, why do you need to do this? Because everybody thinks differently. Now what you do is you take this sine x and you put it back in for r. So you have 2 sine x plus 1 and sine x minus 1. I think it's a visual roadblock in some people's brains to see this quadratic with the sine. Anyway, back to the question. Now what we do is we write 2 sine x plus 1 equals 0 and sine x minus 1 equals 0. And what we've done, everybody, is turn this complex trigonometric equation of 2 sine squared x minus sine x minus 1 equals 0 into 2 simple quadratic equations that into 2 simple or basic trigonometric equations that you learned how to solve yesterday. And what I'm going to be doing as we move forward is relying more and more on the unit circle where appropriate. When we rearrange this equation for sine of x, you get sine of x equals negative 1 over 2. And when you rearrange this for sine of x, you get sine of x equals 1. So could you find a reference angle for each of these? Yes, I'm not going to. Well, I might, I haven't decided. What I'm simply going to do is look at a circle of radius 1. Remember, this is the unit circle. I'm looking for locations where sine of an angle is 1. Now, here's a goofy thing. I'm going to be looking at the y coordinate being 1 because it's sine. The fact that it has x in the equation has nothing to do with x on the unit circle. So there's another adjustment that can be made for some of you. If this is confusing, and I recommend this to a lot of students, from the very beginning use theta instead of x. So where is sine of theta on the unit circle equal to 1? Right here, because that's where y is 1. Why am I focusing on y? Because sine is y. Where is sine of theta negative 1/2? Well, this is negative 1 for y. This is negative 1/2, so it's here and here. These are the 3 locations, which means these are the 3 terminal arms that pass through those points. And now we can answer the question. Let's look at the domain of this. It was from 0 to 2 pi. Well, I'm simply going to fix this first. I'm simply going to ask myself what this angle is. I'm going to ask myself what this angle is. And I'm going to ask myself what this angle is. There are 3 rotation angles that we have to look at. The first one for sine of theta equals 1 is pi over 2. This one right here, and you're looking at the screen, is 1, 2, 3, 4, 5, 6, 7 pi over 6. Continuing on, if this is 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and we're done. I'm not going to do it using a reference angle for this example. If later on you want me to do one with reference angle, that's fine. But I'm going to stick, I think, to the idea that if they are some of these special angles, we need to force ourselves to know the unit circle. Any questions with example 1a? All right. So 1b says, what's the general solution? So we had three solutions. We had theta equals pi over 2. We had theta equals 7 pi over 6. And theta equals 11 pi over 6. The general solutions will be this. I'm not going to write n as an integer for all of these separately. I'm just going to say n is an element of the integer set of numbers. And this goes back to what we talked about yesterday. So does anybody have any questions with 2b? Okay, we're not done with 2b though, because there is a more economical way for you to state all of this. And it's only more economical sometimes. Sometimes this is all you can do. Let me show you that diagram again with our three positions. We had a position here, a position here, and a position here. This is sometimes called the Hippie equation, because it forms a peace sign. I'm just kidding, it's not called the Hippie equation, but it does happen to form a peace sign. And what's interesting about this diagram is that this angle is 120 degrees, and this angle is 120 degrees, and this angle is 120 degrees. These angles are all 120 degrees, which means these terminal arms are all 120 degrees away from each other. And for that reason, what I can do is, for my general solution, I can say pi over 2, which is this one, plus multiples of 2 pi over 3. 2 pi over 3 is 120. So if I go from 90 and add 120, I'm here. Add another 120, add another 120, take away 120. All of these angles are separated by 120 degrees. So you have to watch out for that. Sometimes there's kind of clever ways to summarize all of the solutions. But any questions at all now from example 2? All right, let's take a look at another one then. Solve secant squared theta minus 2 equals 0. Okay, wait. This is a quadratic equation, but there is no linear term. Let me rewrite it for you. It's secant squared of theta, and I'm going to change my x's to theta. I can't look you in the face and tell how you're reacting to this, so maybe to make our lives easier, because we're going to be talking about the unit circle, we simply rewrite the equation, and wherever there's an x, we use theta. Okay, now I don't need to do that, as he writes x. I don't need to do that, and I know there will be some of you that can handle the fact that x in the equation is not the x on the unit circle. But I also know that it's confusing to others. So let's rewrite the equation. Secant squared theta minus 2 equals 0. This is quadratic, and this is constant. There's no linear term. So if you were to look at that picture you took, or maybe you wrote it down earlier, in this particular case, how you solve this is you simply rearrange by moving the constants to the other side and then taking the square root of both sides. So we get secant squared of, so we get secant of theta equals plus or minus root 2. Well, that means now we have two equations. We get secant of theta equals the positive square root of 2 and secant of theta equals the negative square root of 2. Now, if you use the unit circle or use a reference angle approach, you still have to rewrite this as cos of theta equals the reciprocal. Cos of theta equals the reciprocal. So I would like to pause there to let that soak into your brain what we did there. We moved the 2 over, we took the square root, then we reciprocated so we could write cosine. I will do the unit circle and the reference angle approach here. You should recognize on the unit circle that this as a coordinate for x, and we're using x because it's cosine, happens at the 45, that's not very good, happens at the 45-degree angle in quadrant 1 and at the 45-degree angle in quadrant 4. These are the 1 over root 2 comma 1 over root 2 points. You should recognize that negative 1 over root 2 for x happens in the other two quadrants. So do we want degrees here? I think we do. Yeah. So here are our terminal arms. And if I've drawn things right, these will be exactly opposite to each other, and I didn't draw it perfectly, but that's okay. So what are those angles? Well, I'm going to draw them in green. This is one, this is another, this is a third, and this is a fourth. I'm more comfortable working in radians, but in degrees we would have pi over 4. Well, see, think in radians. We would have 45 degrees. This angle would be 180 minus 45, which is 135. This angle would be 180 plus 45, which is 225. And the last angle would be 360 minus 45, which is 315 degrees. How is my arithmetic there?
It looks good.
Okay, thank you, Aaron. So those are the answers. Now, let's just imagine that you wanted to do a reference angle approach. I want you to notice that if you use your calculator to find a reference angle here, or you use your calculator to find a reference angle here, you're going to get the same reference angle. The reason you'll get the same reference angle is you're going to go inverse cos of 1 over root 2. When you find the reference angle here, and I'm hoping that you're starting to nod to yourself or in your head, you're going to get 45 degrees. And if cosine is positive, it's 45 degrees in quadrant 1 and in quadrant 4. If cosine is negative, it's 45 degrees in quadrant 2 and in quadrant 3. So you get the same answers. Now, what's the general solution? Where we asked for a general solution. Oh yeah, also state the general solution. This is a perfect example of us not wanting to say 45 plus multiples of 360, 135 plus multiples of 360, etc. All of these positions are 90 degrees away from each other. If you look at your good copy of the unit circle, these two sets of lines are perpendicular to each other. So what we could say for the general solution, this is the solution from 0 to 360. For the general solution, we could say theta equals 45 degrees plus multiples of 90. Any questions with this example? Okay, number 3. Solve tan squared of x minus 5 tan x plus 4 for angles from 0 to 2 pi to the nearest hundredth of a radian. Okay, so since sometimes it's hard for me to talk and not see you. So if I stutter around a bit, it's because I'm thinking of something. The fact that it says to the nearest hundredth of a radian is a clue to us that these are not going to be pretty angles. These are not going to be angles like 3 pi over 4 or 7 pi over 6. They're going to be angles that are on the unit circle, but they're not the ones that we are familiar with. Okay? If I look at the unit circle and if I look at quadrant 1 of the unit circle and I identify these 3 key points and I say, well, what are the coordinates of this point? You know it's 1/2 root 3 over 2. But if I say, what are the coordinates of this point? The coordinates exist, we just don't know what they are without doing a lot of weird calculations. And that leads me to the following statement, everybody. Since it says to the nearest hundredth of a radian, we're going to be doing this on our calculator in radian mode. First thing I will do to help us out is rewrite this equation with theta. If you want to work with x, that's fine. By the way, if this were a written response in an exam, could you do what I just did? Yes. Now we factor it. Well, I can put a tan of theta here and a tan of theta here and look for 2 numbers that multiply to give 4 and add to give -5. So if that is confusing to you, then what you would do is you would let tan of theta equal something, I'm going to call it a this time, and your equation would become a squared minus 5a plus 4 equals 0, and it would factor into a minus 1, a minus 4. Anyway, now we can solve this. Tan of theta minus 1 equals 0. Tan of theta minus 4 equals 0. This means tangent of theta equals 1. Oh, I lied to you a few minutes ago. Tangent of theta equals 1 will lead us to points that we are familiar with on the unit circle. But I'll get back to that in a second. Tan of theta equals 4 will lead us to points we're not familiar with. Let's do the second part first. Let's find a reference angle in radian mode. That means I need to take inverse tangent of 4 and get I need to make sure I am in radians because we want answers in radians, and go inverse tan of 4 and get 1.33 radians. That's step 1. Step 2, which 2 quadrants can the terminal arm lie in? Well, tangent is positive. Don't forget, on the unit circle, tangent is y over x. Well, it's y over x, period, on the unit circle or otherwise. So where are we going to get a positive for tangent? We're going to get a positive in quadrant 1 because x and y are both positive. And we're going to get a positive for tangent in quadrant 3 because x and y are both positive there. So we draw a reference angle of 1.33 rads. And then we figure out what the rotation angle is, which would be this angle and this angle. So in the first quadrant, if the reference angle is 1.33, the rotation angle is 1.33. In the second quadrant, if the reference angles, or in the third quadrant rather, if the reference angle is 1.33, we need to add pi to that, because from here to here is pi, so we need to add 1.33. Do you get 4.47? Okay, so 4.47. Now what about this one? I would like everybody to find a reference angle for tangent of theta equals 1. That means you're going to go inverse tan of 1. Now, if you are in radians, you are going to get, I think it's 0.57 something, but let's find out. Inverse tan of 1, well, 0.78, that was way off. But it turns out that you should know this is pi over 4. This is actually pi over 4. And the reason why I know that is tangent is y over x. So we are looking at where y divided by x gives you 1. Well, how can that happen? How can you divide two things and get 1? The answer is if they're the same things. So when you look at your unit circle, I'll draw a bigger one this time. When you look at your unit circle, where are y and x equal to each other? Here and here. So that's pi over 4. And 1, 2, 3, 4, 5 pi over 4. You could certainly do it like we did the first equation and get decimal answers, but you don't need to. You could just say pi over 4 and 5 pi over 4. Do we want a general solution? No, we do not. By the way, if we did want a general solution, everybody, then you could say pi over 4 plus multiples of pi, and you could say 1.33 plus multiples of pi, because these two lines will be exactly 180 degrees apart all the time with tangent. Any questions with, I believe that was 4. Any question, no, 3. Any questions with 3? Okay. Number 4. Okay, so wait a minute. Is number 4 quadratic? Yes, because it has a trigonometric that's squared. So we're going to zero the equation. And I get 3 sine squared of x plus 2 sine of x equals 0. We have a quadratic term. We have a linear term. But the constant term is missing in action. There is no constant term. You can't say, well, isn't it plus 0 equals 0? That's not helpful. So now you need to remember what I told you at the beginning of this lesson. That's that when you have this situation, you factor out a common factor. This is very similar for some of you. You might benefit from writing 3p squared plus 2p. You would factor a p out and have 3p plus 2. Which means we have this equation, sine of, I'm going to change it to theta now. I guess I could have changed it earlier, equals 0. And 3 sine of theta plus 2 equals 0. For this one, I'm just going to rewrite it without the brackets. You should know that theta here is 0, pi, etc. Because on the unit circle, sine is the y-coordinate. The y-coordinate is 0 in these two places. So we'll look at the exact answers in a second because I seem to recall we had a degree statement up top. And again, I like working in radians. I guess we'll fix that now. Yeah, 0 to 360. So the first thing I want to ask you is, does 0 degrees make this statement true? And the answer is yes. The sine of 0 gives you 0. Is 180 degrees an angle that makes this statement true? Yes. Is 360 degrees an angle that makes this statement true? Yes. But who's willing to tell me why 360 degrees is not an answer to this question?
The domain says 360 cannot be x.
Right. When you go up to the original domain, it had the, I'm not a big fan of this notation sometimes. It had this, I believe. Is that right, you guys?
Yes.
Okay, so that means 0 degrees is less than or equal to, because of the square brackets. I'm going to stick with my theta since that's what's written on the board here. But this round set of brackets means less than 360. So theta or x, if you're working with x, is not allowed to be 360. With the second equation, we can't use the unit circle. I mean, you have to be adaptable here. You can use the unit circle sometimes, but not all the time. This equation becomes sine of theta equals negative 2/3. So we are stuck with using our calculator and the concept of a reference angle. The reference angle will be the inverse cosine of, the inverse sine of 2/3 now I'm in radians, so I want to be in degrees. We get a reference angle of 41.8 degrees. I don't know what kind of decimals we want. Nearest tenth. Now we look at the negative, the fact that sine is negative, and we identify the two quadrants where sine is negative. That's in quadrant 3 and in quadrant 4, because these are the two quadrants where the y-coordinate is negative and sine is y. I mean, we've come a long way in a couple of days. There's a lot to remember here. What is the actual rotation angle now? Well, it's whatever this is in degrees, and it's whatever this is in degrees. So it looks like we are going to have to take 180 plus 41.8, which gives theta equals 221.8 degrees. And then we will also have to take 360 minus 41.8, which gives 318.2 degrees, I think. Yes?
That's right.
Okay. Thank you, Aaron. So we actually have 4 solutions. We have 0 degrees, 180 degrees. We also have 221.8 degrees and 318.2 degrees. That's it for the day. And again, it's a long lesson. I don't think it's valuable for us. I think it's going to be harmful for your learning if we say, let's work on this for the next half hour and then we'll rush through another lesson. There are the sets of questions that you need to be able to do before we move on. On Monday, we're going to be moving on and looking at graphs of trigonometric functions, which is totally different. So you want to make sure that you end this kind of main section on a high note and you're doing well with this. That's all you're working on. I expect that you stay in the Google Meet until 2:30, unless you get everything done. If you get everything done and you're honest with yourself, then you can sign off of the Google Meet and have a good math-free long weekend. I'll shut my app now and let you guys get to work. And if you have questions, you know the drill. Let me know.